We thought we knew where we were. For thousands of years, humans looked up at a river of stars stretching across the night sky and called it everything. The Milky Way, our galaxy, the universe itself, a single island of light surrounded by eternal darkness. We were not just wrong. We were off by a factor of 2 trillion. In 1929, Edwin Hubble aimed a telescope at a faint smudge in the constellation Andromeda and discovered something that should have been impossible. That smudge was not a cloud of gas. It was not a nearby star system. It was an entire galaxy, sitting more than 2 million light-years away, filled with hundreds of billions of stars we had mistaken for a wisp of nothing. And it was just the beginning. Because once Hubble opened that door, the universe did not stop revealing itself. It kept going, and the more we looked, the more we found, until the number became so large it lost all meaning. 2 trillion galaxies. That is the current estimate for what exists in the observable universe alone. Not 2 trillion stars, 2 trillion galaxies. Each one a system containing billions or even hundreds of billions of suns. Each one separated by distances so vast that light itself takes billions of years to cross the gap. And here is the part that should keep you awake at night. We can only see a fraction of what is actually out there. The rest is hidden behind a veil we may never pull back, held together by forces we cannot see, shaped by substances that make up 95% of reality and remain completely invisible to every instrument we have ever built. So how did we go from thinking we were everything to realizing we are almost nothing? How do you count something you can barely see? And what does it mean to exist in an ocean of light this impossibly large? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. We used to think the universe was small. Not just small in the way you might call your hometown small, but truly, comprehensively, almost insultingly limited. For most of human history, the entire cosmos fit inside a single neighborhood, our neighborhood, the Milky Way. That band of light stretched across the night sky, the one you can still see from dark places far from city lights. That wasn't just part of the universe. It was the universe. Everything else, every star, every glowing smudge, every patch of fuzzy light visible through the best telescopes humanity could build, all of it was assumed to belong to this one enormous island of stars we happen to call home. There was nothing beyond it. No distant shores, no other islands, no vast ocean of space filled with countless other worlds. Just us. One galaxy, one universe, the end. This wasn't ignorance. This was the best science available. The smartest people alive looked through the most powerful instruments ever constructed and saw exactly what you'd expect to see if the Milky Way really was everything. Stars, lots of them, more than anyone could count, and scattered between them, fuzzy patches of light that telescopes could resolve but couldn't quite explain. Some of these patches were clearly inside the Milky Way, glowing clouds of gas lit up by nearby stars. Others were harder to pin down. They had structure. They had spiral arms. They looked almost like miniature versions of the Milky Way itself, which was strange, but not necessarily revolutionary. Plenty of astronomers in the late 1800s and early 1900s simply assumed these spiral nebulae, as they were called, were either gas clouds in the process of forming stars, or perhaps distant, unresolved clusters sitting somewhere on the far side of our galaxy. Big, sure. Distant, maybe, but still part of the same cosmic neighborhood. The alternative was too strange to take seriously. A few voices, going all the way back to the philosopher Immanuel Kant in the 1700s, had suggested that some of these nebulae might actually be island universes. Entire galaxies in their own right, sitting so far away that even their combined light from billions of stars appeared as nothing more than a faint smudge. The idea had a certain poetic appeal. It also had no evidence. Telescopes of the era couldn't resolve individual stars in these nebulae. They couldn't measure distances. They couldn't prove anything one way or the other. So the conservative position, the one that didn't require rewriting the entire scale of the cosmos, was that the Milky Way was it. One galaxy, one universe. Case closed. Then in 1912, a quiet astronomer named Vesto Slipher, working at Lowell Observatory in Arizona, did something no one had done before. He pointed a spectrograph at the Andromeda Nebula, one of the brightest spiral nebulae visible from Earth, and measured how its light was shifted. Spectrographs split light into its component wavelengths, the way a prism splits sunlight into a rainbow. By looking at where the dark absorption lines fall in that spectrum, lines caused by specific elements absorbing specific colors of light, you can tell whether an object is moving toward you or away from you. If it's moving away, the lines shift toward the red end of the spectrum. If it's coming closer, they shift toward blue. This is the Doppler effect. The same reason a train whistle sounds higher as it approaches and lower as it recedes, except with light. Slipher found that Andromeda was moving fast. It was approaching Earth at about 300 kilometers per second, which in cosmic terms is a respectably high speed. But here's the thing. Over the next few years, Slipher measured the spectra of more spiral nebula, and nearly all of them were moving away from us, not just drifting, fleeing. Some of them were receding at speeds upward of 1,000 kilometers per second. That was a problem. Objects inside the Milky Way don't move that fast. Stars in our galaxy orbit the galactic center at a couple hundred kilometers per second, give or take. To see something moving at 1,000 kilometers per second and still be gravitationally bound to the Milky Way would require a galaxy far more massive than anyone believed possible. The speeds Slipher was measuring were escape velocities, the kind of speeds you'd expect from objects that weren't bound to our galaxy at all, objects that were in fact somewhere else entirely. Slipher published his results. A few people noticed, most didn't. The data was strange, sure, but it wasn't conclusive. Maybe these nebulae were being flung out of the Milky Way by some unknown mechanism. Maybe they were remnants of some ancient cosmic event. Maybe the measurements were wrong, the conservative position held. The Milky Way was still everything until 1923. That year, Edwin Hubble, a young astronomer working at the Mount Wilson Observatory in California, gained regular access to the 100-inch Hooker telescope, at the time the largest and most powerful telescope on Earth. He aimed it at the Andromeda Nebula and started taking long-exposure photographs, night after night, building up enough light to see details no one had ever seen before. And in those images, he found something that changed everything. Stars, individual stars, not fuzzy patches, not unresolved blobs of light, actual pinpoint stars sitting inside the spiral arms of Andromeda. And some of those stars were special. Hubble identified Cepheid variables. These are stars that pulse. They brighten and dim on a regular schedule, sometimes over days, sometimes over weeks, with a rhythm as steady as a heartbeat. And here's the key: the period of that pulse, how long it takes to go from bright to dim and back again, is directly related to how luminous the star actually is. A Cepheid that pulses slowly is intrinsically brighter than one that pulses quickly. This relationship had been discovered a decade earlier by Henrietta Leavitt, an astronomer at Harvard who studied Cepheids in the Small Magellanic Cloud. Her work gave astronomers a ruler. If you could measure how fast a Cepheid pulsed, you knew how bright it truly was. And if you knew how bright it truly was, you could compare that to how bright it appeared from Earth and calculate exactly how far away it sat. It was the first reliable cosmic distance measurement that didn't rely on parallax, the slight shift in a star's position as Earth orbits the Sun, which only works for nearby stars. Hubble measured the periods of the Cepheids in Andromeda. He calculated their true luminosities. He compared those to their observed brightness, and he did the math. The result was clear. Andromeda was sitting roughly 1 million light-years away. That number was wrong, as it turned out. Later refinements to the Cepheid calibration showed that Hubble had underestimated the distance. The modern value is closer to 2.5 million light-years, but the error didn't matter. Even at 1 million light-years, Andromeda was sitting far, far outside the Milky Way. The Milky Way itself, by the best estimates of the time, was maybe 100,000 light-years across. Andromeda was 10 times farther than that. It wasn't a gas cloud. It wasn't an unresolved star cluster. It was an entirely separate galaxy. An island universe sitting in the void, completely independent of our own. Hubble sent his results to Harlow Shapley, a prominent astronomer at Harvard who had spent years arguing that the Milky Way was enormous, far larger than earlier estimates suggested, and that the spiral nebulae were probably just outlying parts of it. When Shapley read Hubble's letter, he reportedly said, "Here is the letter that destroyed my universe." That's not hyperbole. Shapley had built his career on a particular vision of the cosmos. A big Milky Way, yes, but still one galaxy, still one universe. Hubble's Cepheids didn't just challenge that vision, they dismantled it. Andromeda was out there. And if Andromeda was out there, then so were all the other spiral nebulae. The universe wasn't a single island, it was an ocean. The shift in scale was dizzying. Imagine spending your entire life believing you live on the only continent. Then one day someone sails over the horizon and comes back with proof that there are thousands of other continents, each one just as large, each one just as real, scattered across an ocean so vast you'll never see most of them. That's what Hubble did to cosmology. He didn't just add a little more space to the map. He shattered the map entirely and replaced it with something incomprehensibly larger. And he wasn't finished. Once you know how far away galaxies are, you can start asking other questions, like, are they moving? And if so, how fast? Hubble already had Slipher's redshift data. Slipher had measured the velocities, Hubble had the distances. Put the two together and you get something extraordinary. The farther away a galaxy sits, the faster it's moving away from us. Not randomly, not chaotically. There's a relationship, a proportionality. Double the distance, double the velocity. This became known as Hubble's law, and it was the observational foundation for one of the most important ideas in modern science. The universe is expanding. Think about what that means. Every galaxy we can see, with a few exceptions like Andromeda, that are close enough to be pulled toward us by gravity, is moving away from us, and the ones that are farther away are moving faster. That's not because we're at the center of some cosmic explosion. It's because space itself is expanding, carrying galaxies along with it, like raisins in a rising loaf of bread. If you rewind that expansion, running the clock backward, everything gets closer together. Keep going, and eventually everything was in the same place, a single point. Infinitely dense, infinitely hot, the beginning, the Big Bang. Hubble's law didn't prove the Big Bang, not immediately, but it gave cosmologists the first direct observational evidence that the universe had a history, that it hadn't always looked the way it does now, that it was evolving. Hubble himself was careful about pushing the cosmological interpretation too far. He was an observer, not a theorist, and he knew that drawing grand conclusions from a handful of data points was risky, but the implications were hard to ignore. If galaxies are all moving away from each other, and if the relationship between distance and velocity holds across the entire observable universe, then the cosmos isn't static, it's dynamic, it's changing. And if it's changing now, it must have been different in the past. That insight reshaped everything. The discovery also did something else. It shrank us. Before Hubble, humanity could at least claim to live in the only galaxy. We were still cosmically insignificant in terms of our size, sure, but at least we had the whole universe to ourselves. After Hubble, we were just one planet, orbiting one star, in one galaxy, in a universe filled with billions of others. The philosophical impact was immediate. If there are that many galaxies, and if each galaxy contains hundreds of billions of stars, then the odds that we're alone, that Earth is the only place where life has ever emerged, start to look absurdly small. Hubble didn't discover alien civilizations. He didn't find evidence of life beyond Earth, but he made the question unavoidable. In a universe this large, this populated with stars and galaxies, how could we possibly be the only ones? There's a detail in the story that doesn't get talked about enough. Hubble's distance estimate for Andromeda was wrong, badly wrong. He was off by more than a factor of 2. And the reason he was wrong is that there are actually 2 types of Cepheid variables, and he didn't know it at the time. One type is intrinsically brighter than the other. Hubble used the wrong calibration, which made Andromeda look closer than it really was. That mistake was corrected in the 1950s by astronomer Walter Baade, who realized the error and recalculated the distances to nearby galaxies, effectively doubling the scale of the universe overnight. But here's the thing. Even with the wrong number, Hubble's conclusion was correct. Andromeda was outside the Milky Way. It was a separate galaxy. The exact distance didn't change that. The philosophical shift had already happened. The universe had already expanded in humanity's collective imagination. Fixing the numbers just made it bigger. What Hubble proved in 1923 wasn't subtle. It wasn't a tweak to an existing model. It was a complete inversion of the cosmological order. The Milky Way went from being everything to being one tiny piece of a vastly larger structure. And that structure, as it turned out, was only the beginning. Because once astronomers accepted that there were other galaxies, the next question became obvious. How many? How far do they go? Is there an edge? And what lies beyond it? Those questions took decades to answer. They required bigger telescopes, better detectors, space-based observatories that could see wavelengths of light blocked by Earth's atmosphere. But the door Hubble opened in 1923 never closed. Every new instrument, every deeper survey, every more sensitive camera pointed at the sky has revealed the same thing. More galaxies, always more galaxies, fainter, farther, older, stranger. The universe refused to run out of them. Standing in that moment in 1923, staring at a photographic plate showing individual stars in Andromeda, Hubble couldn't have known what was coming. He couldn't have predicted the deep field images that would arrive 70 years later, showing thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length. He couldn't have imagined the James Webb Space Telescope peering back to within a few 100 million years of the Big Bang and finding fully formed galaxies already shining in the infant universe. But he opened the door. He proved that the cosmos was larger than anyone had dared to believe. And in doing so, he handed humanity a gift and a burden. The gift was a universe of infinite possibility. The burden was the knowledge that we would never, ever see most of it. Knowing that other galaxies exist is one thing, seeing them is another, and seeing them as they truly are, scattered across distances so vast that their light has been traveling for most of the history of the universe, that requires something extraordinary. Something that didn't exist until the last few decades of the 20th century. It required sending a telescope into space. For all of human history, astronomy was done from the ground. You built the biggest mirror or lens you could afford. You pointed it at the sky, and you dealt with whatever the atmosphere decided to show you. And the atmosphere, it turns out, is not a cooperative partner. It bends light. It blurs images. It absorbs huge chunks of the electromagnetic spectrum before they ever reach the ground. Ultraviolet light, most infrared, X-rays, all of it gets filtered out by layers of air that are very good at keeping us alive and very bad at letting us see the universe clearly. Ground-based telescopes can do remarkable things, but they're always working through a veil. The idea of putting a telescope in orbit where it could see without that interference had been kicking around since the 1940s. It took until 1990 to actually do it. The Hubble Space Telescope launched aboard the Space Shuttle Discovery on April 24, 1990, carrying a 2.4-meter mirror and a suite of instruments designed to observe everything from ultraviolet to near-infrared. It was supposed to revolutionize astronomy. It did, just not right away. The first images Hubble sent back were blurry. Not a little blurry. Catastrophically blurry. Engineers quickly diagnosed the problem. The mirror had been ground to the wrong shape. The error was tiny, less than 1/50th the thickness of a human hair, but at the scale Hubble was designed to operate, that was enough to ruin everything. The telescope that was supposed to peer deeper into space than any instrument in history couldn't focus. NASA's reputation took a beating. Late-night talk show hosts had a field day. The Hubble Space Telescope became a punchline. Then in December 1993, NASA launched a repair mission. Astronauts aboard the Space Shuttle Endeavour spent 10 days installing corrective optics, essentially giving Hubble a pair of glasses. When the first post-repair images came down, the difference was immediate, sharp, clear, perfect. Hubble could finally see, and once it could see, astronomers started asking what they should point it at. One of the strangest proposals came from the telescope's director, Robert Williams. He wanted to aim Hubble at nothing, not at a nearby galaxy, not at a known cluster of stars, not at anything that had ever been catalogued or studied. He wanted to pick a patch of sky so dark, so empty, so devoid of obvious targets that no astronomer in their right mind would waste precious telescope time looking at it. Then he wanted to stare at that patch for 10 straight days. The idea sounded insane. Hubble's observing time was the most valuable scientific resource in the world. Every astronomer on the planet wanted a piece of it. Proposals were carefully vetted, prioritized, fought over. Time on Hubble was measured in minutes, and here was Williams suggesting they burn more than 200 hours on a blank patch of sky, with no guarantee they'd see anything interesting. Most of the advisory committees thought it was a waste. Williams did it anyway. He had the authority as director to allocate a chunk of discretionary time, and he used it. In December 1995, Hubble turned toward a tiny region in the constellation Ursa Major, just above the bowl of the Big Dipper, and started collecting light. The field was absurdly small, 2.6 arc-minutes across. That's about 1/24th of the diameter of the full moon. If you held a grain of sand at arm's length, it would cover roughly the same amount of sky. From the ground, that patch looked empty. A few stars maybe, nothing else, just black. But Hubble didn't look for a few minutes. It looked for 10 days, and it didn't just take one picture. It took 342 separate exposures through different filters, capturing light across ultraviolet, visible, and near-infrared wavelengths. Then computers stacked all those images together, aligning them pixel by pixel, building up signal while averaging out noise. The final result was a composite image representing more than 1 million seconds of total exposure time. When the Hubble Deep Field was released to the public in January 1996, it broke astronomy. That empty patch of sky wasn't empty, it was full, absolutely packed with galaxies. The first counts put the number at around 1,500. Later analysis pushed it closer to 3,000. Almost every blob of light in the image, aside from maybe 20 foreground stars sitting inside our own Milky Way, was a galaxy. Some were nearby, cosmically speaking, sitting a few 100 million light-years away. Others were so distant their light had been traveling for more than 12 billion years. 12 billion. The universe itself is only about 13.8 billion years old. Hubble was seeing galaxies that had formed when the cosmos was still in its infancy, less than 2 billion years after the Big Bang. This is where the idea of looking back in time stops being a metaphor and becomes literal. Light travels fast, but space is big, really big. When you look at the sun, you're seeing it as it was 8 minutes ago, because that's how long it takes light to cross the 93 million miles between the sun and Earth. Look at the nearest star beyond the sun, Proxima Centauri, and you're seeing it as it was 4 years ago. Look at the Andromeda galaxy, and you're seeing it as it was 2.5 million years ago. The light hitting your eyes right now left Andromeda before humans existed, before our genus existed, before most of the species we recognize as human ancestors had even evolved. Now, extend that principle across billions of light years. The galaxies in the Hubble Deep Field aren't just far away. They're far in the past. The most distant objects in that image are showing us what the universe looked like when it was young. Not theoretically young, actually young. Those galaxies, as they appear in the Hubble Deep Field, don't look like that anymore. They've had 12 billion years to evolve, to merge with other galaxies, to form new stars, to change. Some of them probably don't exist as independent objects anymore. They've been swallowed by larger galaxies or torn apart by gravitational interactions. The light we're seeing is a fossil, a snapshot of something that happened so long ago that entire galaxies have lived and died in the time it took that light to reach us. Think about what that means for understanding cosmic history. Astronomers can't watch a single galaxy evolve over billions of years. Human lifetimes are too short. Civilizations are too short. But they can look at galaxies at different distances, which correspond to different moments in time, and piece together the story. The Hubble Deep Field gave them a timeline. Nearby galaxies, the ones that are relatively close and whose light left them recently, show what mature galaxies look like. Smooth, well-organized, full of old red stars in some cases, or still forming stars in others, but clearly settled into stable structures. The distant galaxies, the ones whose light has been traveling for 10 or 12 billion years, look different, smaller, irregular, chaotic, clumpy. These are galaxies in the process of forming, still pulling themselves together out of clouds of gas, still figuring out how to be galaxies. The Hubble Deep Field didn't just show astronomers what the early universe looked like, it gave them a laboratory. They could count how many galaxies existed at different epochs. They could measure their sizes, their brightness, their colors. They could estimate how fast stars were forming inside them. They could watch, in a statistical sense, as the universe grew up. The data that came out of that one 10-day observation triggered hundreds of follow-up studies. Papers are still being published based on Hubble Deep Field data decades later. William's gamble paid off so spectacularly that NASA did it again. In 2004, Hubble aimed at an even smaller patch of sky in the constellation Fornax and stared for even longer. This time, the exposure ran for about 1 million seconds, spread over 4 months. The resulting image, called the Hubble Ultra Deep Field, went deeper than the original. It captured light from galaxies sitting at redshifts up to around 8 or 9, meaning their light had been traveling for over 13 billion years. The universe in those images was less than 1 billion years old. Some of the galaxies in the ultra-deep field are among the most distant objects ever observed in visible light, and there are about 10,000 of them. 10,000 galaxies in a patch of sky you could cover with a pinhead held at arm's length. Let that settle for a second. 10,000 galaxies in one tiny corner of the sky. The entire sky contains about 41,000 square degrees. The Hubble Ultra Deep Field covers about 11 square arc minutes, which is about 3/millionths of 1 square degree. Scale that up. If the rest of the sky is even remotely similar in galaxy density to what Hubble saw in that field, and there's no reason to think it isn't, then the observable universe contains somewhere in the ballpark of 200 billion galaxies, maybe more. And each one of those galaxies contains hundreds of billions of stars. The math gets uncomfortable fast. But Hubble had limits. It could see far, but not far enough. The problem wasn't the mirror. The problem was wavelength. As the universe expands, light traveling through it gets stretched. This is redshift, the same effect Edwin Hubble used to discover that galaxies are moving away from us. The farther away an object is, the more its light has been stretched, shifting from shorter wavelengths, blue and ultraviolet, to longer wavelengths, red and infrared. By the time light from the most distant galaxies in the early universe reaches us, it's been stretched so much that it's no longer visible to the human eye. It arrives in the infrared, a part of the spectrum Hubble's instruments could detect, but not with great sensitivity. To see the very first galaxies, the ones that formed in the first few 100 million years after the Big Bang, you need a telescope designed specifically to observe in the infrared. You need something bigger, colder, and more sensitive than Hubble. You need the James Webb Space Telescope. Webb launched on December 25, 2021, aboard an Ariane 5 rocket from French Guiana. It didn't go into orbit around Earth. It traveled to a point in space called the second Lagrange point, about 1 million miles away, where the gravitational pull of the Earth and the Sun balance out. From there, Webb could keep its massive sun shield pointed toward the Sun, Earth, and Moon simultaneously, blocking their heat and light, and keeping its instruments at temperatures cold enough to detect faint infrared signals from the edge of the universe. The mirror is 6.5 meters across, nearly 3 times the diameter of Hubble's, giving it more than 6 times the light collecting area. And every single instrument on board is optimized for infrared. The first deep field image from Webb was released in July 2022. It showed a galaxy cluster called SMACS 0723 as it appeared 4.6 billion years ago. That's not particularly early in cosmic terms, but the cluster's gravity acted as a lens, bending and magnifying light from even more distant galaxies sitting behind it. Some of the galaxies visible in that image are more than 13 billion light-years away. Their light left them when the universe was less than 1 billion years old, and they're not faint smudges. They're sharp, detailed, clearly resolved structures. Spiral arms, star-forming regions, dust lanes. Webb can see features in these galaxies that Hubble could barely detect. Then Webb started doing targeted deep observations of its own, and the results were strange. Astronomers expected to find galaxies in the early universe. That wasn't the surprise. The surprise was how many there were, how bright they were, and how mature some of them looked. Standard models of galaxy formation predicted that the first galaxies would be small, dim, chaotic, proto-galaxies still in the process of assembling. Instead, Webb found massive galaxies, some weighing billions of times the mass of the Sun, sitting comfortably at redshifts of 10, 12, even 14. That corresponds to a time when the universe was only a few 100 million years old. According to the models, there shouldn't have been enough time for galaxies that large to form. Stars take time to ignite. Gas clouds take time to collapse. Dark matter halos take time to pull matter together. The early universe should have been messy, unformed, primitive. Webb showed otherwise. One galaxy in particular, spotted at a redshift of around 14, appeared to contain stars that were already somewhat evolved. Not the very first generation of stars, which should be composed purely of hydrogen and helium, but stars with heavier elements in their spectra. That means earlier generations of stars had already formed, lived their lives, exploded, and seeded the surrounding gas with carbon, oxygen, and other elements. All of that had to happen in less than 300 million years. The timeline is tight, uncomfortably tight. It's not impossible, but it forces astronomers to reconsider how quickly galaxies can assemble in the early universe. The other surprise was how common these early galaxies seemed to be. Hubble could detect a few candidates at extreme distances, but they were rare, sitting right at the edge of detectability. Webb sees them everywhere. Almost every deep field image Webb has taken contains galaxies at redshifts above 10. They're not anomalies, they're not flukes, they're a normal part of the early universe. That changes the math on how many galaxies formed in the first billion years after the Big Bang. It might also change our understanding of the role supermassive black holes played in early galaxy evolution. because several of these early galaxies show signs of harboring active black holes at their centers, something else that shouldn't have had time to grow that large that fast. There's a philosophical weight to these images that's easy to miss if you just look at them as pretty pictures. Every galaxy in a deep field, whether it's Hubble's or Webb's, is a place, an actual location in space containing billions or trillions of stars, many of which probably have planets, some of which might be capable of supporting life. And the light reaching us from those galaxies is ancient. It left its source billions of years ago. If there were civilizations on planets orbiting stars in those galaxies at the moment that light was emitted, they're long gone now. Their stars have aged, their galaxies have changed. In some cases, their galaxies have collided with others and merged into entirely new structures. We're not seeing those galaxies as they are. We're seeing ghosts. And here's the part that really twists the knife. They're seeing us as ghosts too. If someone in one of those distant galaxies happened to point a telescope toward the Milky Way right now, they wouldn't see us. They'd see the Milky Way as it was billions of years ago, long before the sun formed, long before the solar system existed, long before Earth had cooled enough to have liquid water on its surface. They'd be looking at a galaxy full of stars that are almost entirely different from the stars we see when we look up at night. Our sun wouldn't be there. We wouldn't be there. The light carrying information about our existence hasn't reached them yet. It won't for billions of years. And by the time it does, assuming anyone is still around to see it, we'll be as ancient to them as those early galaxies are to us. The deep fields don't just expand the universe spatially, they expand it temporally. They turn astronomy into archaeology. Every observation at high redshift is an excavation, digging deeper into the past, uncovering layers of cosmic history that would otherwise remain hidden. And the deeper we dig, the stranger it gets. Hubble showed us that the early universe was full of galaxies. Webb is showing us that those galaxies were more complex, more varied, more mature than we thought possible. That's not a comfortable finding if you're a cosmologist trying to build models that explain how everything came to be. It means the models need work. It means there are processes we don't fully understand. It means the universe is still capable of surprising us, and it means we're not done looking. The deep fields we have now, stunning as they are just the beginning. Webb has only been operational for a few years. It's going to keep staring at the sky, finding fainter galaxies, pushing further back in time. At some point, it will hit a wall. There's a moment in cosmic history, about 380,000 years after the Big Bang, before which the universe was opaque. No stars had formed yet. No galaxies existed. The cosmos was just a hot, dense fog of hydrogen and helium, glowing uniformly in every direction. That glow is still visible today as the cosmic microwave background, the faint radio hiss left over from the Big Bang itself. Webb can't see past that. No telescope can. But between that wall and now, between the moment the first stars ignited and the present day, there are 13.8 billion years of history waiting to be explored. And every time we point a telescope at a new patch of sky and let it soak up light for days or weeks or months, we pull more of that history into focus. The galaxies are out there, billions of them, trillions maybe. And the only way we'll ever know how many, the only way we'll ever see what they looked like in their youth, in their prime, in their old age, is to keep looking. The deep fields proved that the universe is willing to reveal its secrets if we're patient enough to wait for the light to arrive. Looking at thousands of galaxies in the Hubble Deep Field is one thing. Counting all of them is another problem entirely. Because here's the uncomfortable truth. We can't. Not directly, not even close. The universe is too big, the galaxies too numerous, and the limits of our telescopes too severe for us to sit down with a clicker and tally them up one by one. And yet, astronomers will tell you with a straight face that the observable universe contains somewhere in the neighborhood of 2 trillion galaxies. Not hundreds of billions, trillions. 2 million galaxies scattered across space, each one a separate island containing anywhere from a few million to several trillion stars. That's the number floating around in the scientific literature right now. And the question you should be asking is how anyone could possibly know that. Because we've only looked at a few tiny patches of sky in any real detail. We've taken maybe a handful of deep field images covering areas smaller than grains of sand held at arm's length. The rest of the sky remains largely unexplored at those depths. So how do you go from seeing a few thousand galaxies in a couple of narrow fields to claiming there are 2 trillion galaxies in total? The answer involves a lot of math, a lot of assumptions, and a lot of very careful guessing. But it's not wild guessing. It's educated, methodical, peer-reviewed guessing, the kind that holds up under scrutiny most of the time. Let's start with what we actually know. The Hubble Deep Field, that first groundbreaking 10-day exposure released in 1996, showed about 3,000 galaxies. Later refinements of the data pushed that number a bit higher, but 3,000 is a reasonable working figure. The field itself covered roughly 2.6 arc-minutes, which translates to about 1/24 millionth of the entire sky. If you assume, and this is a big assumption but a reasonable one, that the rest of the sky looks statistically similar to that patch, you can scale up. Multiply 3,000 galaxies by 24 million, and you get 72 billion galaxies. That was the early estimate. 70 to 80 billion galaxies in the observable universe, give or take. It was a staggering number at the time. It also turned out to be way too low. The problem wasn't the math. The problem was what Hubble couldn't see. Telescopes have limits. They can only detect objects above a certain brightness threshold. Anything fainter than that threshold just disappears into the background noise. And the Hubble Deep Field, as deep as it was, still had a cutoff. There were galaxies sitting in that same patch of sky that were simply too faint for Hubble to pick up. Small galaxies, distant galaxies, galaxies whose light had been stretched so far into the infrared by the expansion of the universe that Hubble's visible light cameras couldn't register them. Those galaxies were there. Hubble just couldn't see them. And if Hubble couldn't see them in the deep field, it couldn't see them anywhere, which meant the 70 billion number was incomplete. So astronomers did what they always do when they hit the limits of direct observation. They started modeling. They built simulations of how galaxies form and evolve over cosmic time. They plugged in everything they knew about star formation, gas dynamics, dark matter halos, gravitational interactions, the whole machinery of galaxy assembly. Then they ran the simulations forward from the early universe to the present day and counted how many galaxies should exist at different masses and brightnesses. The models predicted that there should be a lot more small, faint galaxies than large, bright ones. That's consistent with what we see in the nearby universe. Dwarf galaxies outnumber giant galaxies by a huge margin. Our own Milky Way has dozens of small satellite galaxies orbiting it, and we keep finding more. But dwarf galaxies are hard to spot at large distances. They don't put out much light. If you're sitting billions of light years away, a dwarf galaxy is essentially invisible unless you stare at it for a very long time with a very sensitive instrument. The models suggested that the Hubble Deep field was only scratching the surface. For every galaxy Hubble detected, there might be 10 or 20 or even 100 smaller, fainter galaxies lurking below the detection limit. If that were true, the total number of galaxies in the observable universe wasn't 70 billion. It was much, much higher. But how do you test that? How do you confirm the existence of galaxies you can't see? One way is to look at the cosmic background light. This is the diffuse glow of all the unresolved light in the universe. When you point a telescope at a patch of sky and measure the total brightness, even after subtracting out all the individual stars and galaxies you can identify, there's still a faint background glow left over. That glow has to be coming from something. And the most likely explanation is that it's coming from all the faint, distant, unresolved galaxies that are too dim to detect individually but collectively add up to a measurable signal. By carefully measuring the cosmic background light across different wavelengths and comparing it to the light coming from all the galaxies we can see, astronomers can estimate how much light is missing. How much of the total glow is coming from galaxies below the detection limit? The numbers from those measurements suggested that Hubble was missing a lot. Somewhere between half and 2/3 of all the light in the universe was coming from galaxies that weren't showing up in the deep field images. That implied a huge hidden population of faint galaxies. And if you extrapolate from that, accounting for all the small dim galaxies that Hubble couldn't detect, the total galaxy count shoots up, not to 100 billion, to several hundred billion, maybe more. Then in 2004, Hubble went deeper. The ultra-deep field pushed the exposure time to nearly 1 million seconds, spread over 4 months. It covered a slightly different patch of sky in the constellation Fornax, and it reached further back in time and detected fainter objects than the original deep field. The result was about 10,000 galaxies in a single image. 10,000. And again, that was just what Hubble could see. The models predicted that for every galaxy in the ultra-deep field, there were probably dozens more sitting below the brightness cutoff. The population of faint dwarf galaxies in the early universe was expected to be enormous. These weren't the massive, bright galaxies that dominated the nearby universe. These were the building blocks. small clumps of stars and gas that would eventually merge together over billions of years to form the larger galaxies we see today. Hierarchical assembly, that's the technical term. Galaxies grow by eating smaller galaxies. It's violent, it's messy, and it's been happening since the first stars lit up. By the mid-2000s, the consensus estimate for the total number of galaxies in the observable universe had climbed to around 100 to 200 billion. That number got repeated in textbooks, documentaries, press releases. It became the standard answer, and for a while it held. Then, in 2016, a team led by Christopher Consolis at the University of Nottingham published a paper that revised the number upward, dramatically upward. They combined data from Hubble's deep fields with new theoretical models that tried to account for the full population of galaxies across all masses and all epochs of cosmic history. They used a technique called number density evolution, which tracks how the density of galaxies changes over time as the universe expands and galaxies merge. Their conclusion was that the observable universe contains roughly 2 trillion galaxies, not 200 billion, 2 trillion. 10 times higher than the previous estimate. The reaction in the astronomy community was mixed. Some thought the new number was robust, that it finally accounted for all the faint galaxies that earlier estimates had missed. Others were more skeptical, pointing out that the uncertainties in the models were large and that the number could easily be off by a factor of 2 or 3 in either direction. But the 2 trillion figure stuck. It made headlines. It became the new standard answer, at least in popular science, and it underscored a basic truth about this kind of work. We are not counting galaxies the way you count apples in a basket. We are sampling a tiny fraction of the sky, building statistical models of what we think the rest of the sky looks like, and extrapolating from there. The error bars are huge, the assumptions are many, and the final number is only as good as the models we're using. Here's what makes this so tricky. The observable universe isn't everything. It's just the part of the universe we can see. Light from more distant regions hasn't had time to reach us yet, because the universe is only 13.8 billion years old, and light only travels so fast. There's a horizon, a boundary beyond which we can't see, not because there's nothing there, but because the light from those regions simply hasn't arrived yet. The size of the observable universe is determined by the speed of light and the age of the universe. Do the math, and you get a sphere roughly 93 billion light-years in diameter, centered on Earth. That's the volume we're talking about when we say 2 trillion galaxies. But the actual universe, the full cosmos, is almost certainly much larger than that, maybe infinitely larger. If that's true, then 2 trillion galaxies is just the galaxies in our little patch, a sample, not the full count. The total number of galaxies in the entire universe, not just the part we can see, could be orders of magnitude higher, or it could be infinite. We don't know. We can't know. The only number we can ever hope to estimate is the number within the observable horizon, and even that is hard. One of the big challenges is that galaxies aren't static. They're constantly changing. Stars are born, stars die, gas gets consumed, galaxies collide and merge. A galaxy that existed 10 billion years ago might not exist as an independent object today. It might have been swallowed by a larger neighbor, or it might have merged with another galaxy to form something entirely new. When astronomers count galaxies in the Hubble Deep field, they're not counting the same population at every distance. Nearby galaxies are being seen as they are now, or at least as they were a few million or a few 100 million years ago. Distant galaxies are being seen as they were billions of years ago, when the universe was younger and the galaxy population looked very different. So when you try to add up all the galaxies across all distances, you're not just counting objects in space, you're counting objects across time. Some of the galaxies you're counting in the distant universe have since merged and are now part of larger galaxies in the nearby universe. If you're not careful, you could end up double counting, or undercounting, or just getting confused. The models that Consolus's team used tried to account for this by tracking the merger history of galaxies over cosmic time. They estimated how many small galaxies in the early universe merged together to form the larger galaxies we see today. Then they added up the total number of distinct galaxies that have ever existed within the observable horizon, whether they still exist as independent objects or not. That's where the 2 trillion number comes from. It's not 2 trillion galaxies today. It's 2 trillion galaxy equivalents integrated over the full history of the observable universe. Some of those galaxies are still around. Many have merged. The distinction matters, but it also gets glossed over in a lot of popular accounts. When someone says there are 2 trillion galaxies, what they usually mean is that if you could freeze time at every point in cosmic history and count all the distinct galaxies that existed at each moment, then add them all up without double counting, you'd get something close to 2 trillion. It's a cumulative count, not a snapshot. And here's another wrinkle. The definition of what counts as a galaxy isn't as clear-cut as you might think. Is a small clump of a few million stars orbiting a larger galaxy its own galaxy, or just a satellite? At what point does a dense star cluster stop being a cluster and start being a dwarf galaxy? There's no sharp line. Astronomers have conventions, sure. They use criteria like total mass, size, whether the object is gravitationally bound, whether it has its own dark matter halo. But at the edges, the definitions get fuzzy. And when you're trying to count objects across the entire observable universe, including the faintest, dimmest, most marginal cases, those fuzzy edges add up to a lot of uncertainty. The Hubble Extreme Deep Field, released in 2012, tried to push even deeper. It combined over 2,000 individual exposures from Hubble, including data from the original deep field, the ultra-deep field, and several other surveys. The final image showed about 5,500 galaxies and reached back to within a few 100 million years of the Big Bang. Some of the galaxies in the XDF are so distant that their light has been traveling for over 13 billion years. We're seeing them as they were when the universe was less than 5% of its current age. At those distances, galaxies look primitive, small, irregular, often clumpy and asymmetric. These are the protogalaxies, the seeds that would eventually grow into the massive, well-ordered spirals and ellipticals we see nearby. And there are a lot of them. The XDF showed that the early universe was absolutely teeming with small star-forming galaxies, far more than anyone expected. That finding supported the idea that most of the galaxies in the universe are small and faint. The big bright galaxies get all the attention because they're easy to see, but numerically they're the minority. The universe is dominated by dwarfs. NASA's Hubble Legacy Field, published in 2019, went even further. It combined nearly 7,500 Hubble exposures taken over 16 years, stitching together data from multiple surveys into a single mosaic covering a slightly larger area than the previous deep fields. The legacy field contains about 265,000 galaxies spanning 13.3 billion years of cosmic history, 265,000 in one image. And that's still just a tiny sliver of the sky. The legacy field covers an area roughly the size of the full moon, which sounds big until you remember that the full sky contains about 41,000 square degrees, and the full moon only covers about half a degree. The legacy field is a fraction of a percent of the total sky, and even in that fraction, Hubble is still missing most of the faint galaxies. The 265,000 galaxies in the legacy field are just the ones bright enough to detect. The models predict that there are many times more galaxies in that same region, sitting below Hubble's detection threshold. So how do astronomers estimate how many galaxies they're missing? One method is to take deep field data and bin the galaxies by brightness. Count how many galaxies fall into each brightness range. Then plot that distribution on a graph. What you typically see is that as you go to fainter brightnesses, the number of galaxies increases a lot. For every bright galaxy, there are 10 or 100 faint ones. The distribution follows a power law. And if you extrapolate that power law down to brightnesses below what your telescope can detect, you can estimate how many faint galaxies should be there, even though you can't see them. The trick is knowing where to stop extrapolating. Does the power law keep going forever? Probably not. At some point, there has to be a lower limit. Galaxies below a certain mass just don't form efficiently. The gas is too hot, or radiation from nearby stars blows it away before it can collapse. Or dark matter halos below a certain size can't hold on to their gas long enough to make stars. So the faint end of the galaxy population doesn't keep rising forever. It flattens out. But where it flattens out and how steeply is still a matter of debate. Different models give different answers, and that uncertainty propagates directly into the total galaxy count. Another approach is to use what's called the galaxy luminosity function. This is a mathematical description of how many galaxies exist at each level of brightness. Measure the luminosity function in the nearby universe where you can see everything clearly. Then use models of galaxy evolution to predict how that function changes at earlier times when the universe was younger. Then integrate the luminosity function over all brightnesses and all redshifts, and you get a total galaxy count. The problem is that the models of galaxy evolution aren't perfect. They rely on assumptions about star formation rates, gas accretion, feedback from supernovae and black holes, the effects of dark matter, all of which are only partially understood. Change the assumptions and the predicted galaxy count changes, sometimes by a lot. The 2 trillion number from Consolise's team came from one particular set of assumptions. Other teams using different models have gotten different numbers, some higher, some lower. The uncertainty is real and it's large, probably a factor of 2 or 3 at least, maybe more. The James Webb Space Telescope is starting to chip away at that uncertainty. Webb's infrared sensitivity lets it see galaxies that were completely invisible to Hubble. Galaxies whose light has been redshifted so far into the infrared that Hubble's cameras just couldn't pick them up. In the first year of Webb operations, multiple teams reported finding large numbers of galaxies at redshifts above 10, 11, even as high as 14. These are galaxies forming in the first few 100 million years after the Big Bang. Hubble saw hints of a few candidates at those distances, but Webb is finding them by the dozens. That suggests the early universe had even more galaxies than the models predicted, which could push the total count higher. Or it could mean that the models were overestimating the number of faint galaxies at later times and underestimating them at early times, in which case the total might stay roughly the same, but the distribution changes. It's too early to say. Webb has only been operating for a couple of years. The data is still being analyzed. The full implications for galaxy counts won't be clear for another few years at least. One thing Webb has made clear is that the missing galaxies problem is real. Even in Webb's deepest images, you can see that the background between the resolved galaxies isn't perfectly dark. There's a faint diffuse glow, especially in the infrared. Some of that glow is instrumental noise, sure, but a lot of it is real light coming from galaxies that are too faint or too small to resolve individually. They're blending together into a kind of cosmic fog. That fog represents all the light from all the galaxies that no telescope has ever been able to separate out and count. And until we can either build telescopes sensitive enough to resolve those galaxies or develop better statistical methods to account for them, the total galaxy count will remain uncertain. Interestingly, the shift from 200 billion to 2 trillion galaxies didn't come from a sudden improvement in telescope technology. It came from better modeling. Hubble's data didn't change. What changed was our understanding of how much we were missing. The deep fields showed us a sample. The models told us how to scale that sample up to a full population. And the models said we were missing a lot more than we thought. That's how science works sometimes. You don't always need new data to get new answers. Sometimes you just need a better way of interpreting the data you already have. The 2 trillion number might be revised again in the future. It probably will be, but the trend is clear. Every time we look deeper, every time we push our telescopes to their limits, every time we refine our models and our statistical techniques, the number goes up, not down, up. The universe keeps revealing more galaxies, more structure, more complexity, and we're still only scratching the surface. There's something profoundly humbling about this. We've built telescopes that can see across 13 billion years of cosmic history. We've imaged individual galaxies forming in the infant universe. We've counted hundreds of thousands of galaxies in tiny patches of sky. And after all that, after all the deep fields and all the modeling and all the careful analysis, we still can't give you a precise number for how many galaxies there are. The best we can do is say it's somewhere in the trillions, maybe 2 trillion, maybe more, maybe less. The error bars are enormous, and that's okay, because the point isn't to get an exact count. The point is to understand the scale, to grasp, in some visceral way, just how absurdly large and populated the universe really is. 2 trillion galaxies, each one a separate world, each one containing billions or trillions of stars, each star potentially hosting planets, each planet potentially harboring life. The numbers stop meaning anything after a while. They're too big, too abstract, but the implication is clear. We are not alone in the universe. Not in the sense that there's definitely alien life out there, though the odds seem pretty good, but in the sense that we are not the only galaxy, not even close. We are one of trillions, a single note in a symphony so vast that we can't even hear most of it. And everything we've learned so far, every galaxy we've counted, every deep field we've taken, is just the opening movement. The rest of the universe is still out there, waiting to be explored. And here's the kicker. All of this, every galaxy we've talked about, every deep field image, every statistical model, every estimate of 2 trillion galaxies, all of it is just the visible matter, the stuff that emits light, the stuff we can see. There's something else out there, something that doesn't shine, something that doesn't interact with light at all, but whose gravitational pull shapes every galaxy, every cluster, every structure we've ever observed. We call it dark matter, and it outnumbers the stuff we can see by a factor of 5 to 1. Which means the universe we've been counting, the universe of galaxies and stars and gas, is just the tip of the iceberg. The rest is invisible. And it's bigger than everything else combined. All of this counting, all of these deep fields, all of these estimates of 2 trillion galaxies scattered across the observable universe, they all rest on one basic assumption, that the galaxies are real, that the light we see is coming from collections of stars held together by gravity, that the mass we infer from the brightness of those stars is actually there. For most of the 20th century, that assumption seemed safe. You could see the stars, you could measure their brightness, you could calculate how much mass they contained based on how much light they put out. The math worked, the galaxies stayed together, everything made sense. Until astronomers looked closer, and what they found was that the galaxies shouldn't be staying together at all. The stars were moving too fast, the mass wasn't where it was supposed to be, and the only way to make the numbers work was to admit that most of what holds a galaxy together is something we can't see, something that doesn't emit light, something that doesn't absorb light, something that doesn't interact with light at all. We call it dark matter, and it's not a footnote, it's not a minor correction to the models. It's most of the universe, about 5 times more massive than all the stars, gas, planets and dust we've ever observed. Which means that everything we've been counting, every galaxy in every deep field, every estimate of how much ordinary matter exists in the cosmos, is just the visible tip of a much larger iceberg. The rest is invisible, and it's holding everything together. The story starts with a woman who spent decades staring at galaxies that weren't behaving. Vera Rubin was an astronomer at the Carnegie Institution in Washington, and in the 1970s she was doing something that sounds almost boring, measuring how fast stars orbit inside spiral galaxies. It's the kind of work that doesn't make headlines. You point a spectrograph at a galaxy, measure the Doppler shift of light coming from stars at different distances from the center, and calculate how fast those stars are moving. Then you plot the results on a graph, rotation speed versus distance. That's it. That's the job. And for most galaxies, the expectation was simple. Stars closer to the center should orbit faster. Stars farther out should orbit slower. Just like planets in our solar system, Mercury orbits the Sun much faster than Earth. Earth orbits faster than Jupiter. Jupiter orbits faster than Neptune. The farther you get from the Sun, the weaker the gravitational pull and the slower the orbital speed. That's basic Newtonian mechanics. Gravity weakens with distance. The same principle should apply to galaxies. Most of the mass in a spiral galaxy is concentrated in the bright central bulge, so stars near the center should feel a strong gravitational pull and orbit quickly. Stars out in the spiral arms, far from the center, should feel a weaker pull and orbit slowly. The rotation curve, the graph showing speed versus distance, should drop off as you move outward. That's what the equations predicted. That's what every model of galaxy dynamics said should happen. That's not what Rubin found. She looked at spiral galaxy after spiral galaxy, and the rotation curves were flat, not dropping, flat. Stars in the outer regions of these galaxies were moving just as fast as stars near the center. In some cases, they were moving even faster, and that made no sense. If you see something orbiting faster than it should, given the amount of mass you can account for, there are only two possibilities. Either the laws of gravity are wrong, or there's more mass than you're seeing. Rubin trusted gravity, so she started calculating how much unseen mass would be needed to explain the flat rotation curves. The answer was shocking. For the galaxies she studied, the amount of invisible mass required was enormous. 5 times the visible mass, 10 times in some cases. The stars you could see, the glowing gas clouds, the dust, all of that was just a small fraction of the total. Most of the galaxy's mass was something else. Something that didn't shine. Something that exerted gravity but emitted no light. Dark matter. Rubin wasn't the first person to suggest that invisible mass might be lurking in the universe. That idea went back to the 1930s. A Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a large group of galaxies bound together by gravity. He measured how fast the individual galaxies were moving within the cluster and used that to calculate the cluster's total mass. Then he added up the mass of all the visible galaxies and compared the two numbers. They didn't match, not even close. The galaxies were moving so fast that the cluster should have flown apart long ago unless there was far more mass holding it together than he could see. Zwicky called the missing mass dunkle materie, dark matter, but his idea didn't gain much traction. Zwicky had a reputation for being difficult, and his estimates were rough. The uncertainties were large enough that most astronomers dismissed the result as a measurement problem. Maybe the galaxies weren't moving as fast as he thought. Maybe the cluster was more massive than it appeared. Maybe he'd made a mistake somewhere in the math. The simplest explanation was that Zwicky was wrong, so the field moved on. For 40 years, the idea of dark matter sat on the shelf, mostly ignored. Rubin's work was different. She wasn't measuring a distant cluster with large uncertainties. She was measuring individual galaxies, close enough to resolve in detail. The rotation curves were clean, precise, repeatable. Other astronomers checked her work. They looked at other galaxies. They found the same thing, flat rotation curves. Everywhere. Galaxy after galaxy, the stars in the outer regions were moving too fast. The pattern was undeniable, and the only way to explain it was to accept that galaxies are surrounded by enormous halos of invisible mass, halos that extend far beyond the visible disk of stars. Halos that contain 5 to 10 times more mass than all the ordinary matter you can see. The visible galaxy, the part that shows up in photographs, is just the bright center of a much larger dark structure. Think of it like an iceberg. The part above water is the stars, the part below water is the dark matter, and the part below water is vastly larger. Rubin's discovery was initially hard to swallow. The idea that 90% of a galaxy's mass could be invisible felt almost ridiculous. How could something that massive remain completely undetected? But the data kept piling up. Other lines of evidence started pointing in the same direction. Galaxy clusters, for instance. Zwicky had been right all along. When astronomers measured the total mass of clusters using multiple methods, gravitational effects, X-ray emissions from hot gas, the motion of galaxies within the cluster, the numbers all agreed. Clusters contained far more mass than could be accounted for by visible matter. The missing mass was real, and it was everywhere. Then came gravitational lensing. Einstein's theory of general relativity predicts that massive objects bend space, and light traveling through that bent space follows a curved path. If a galaxy or a cluster of galaxies sits between us and a more distant object, the gravity of the foreground object acts like a lens, bending the light from the background object and distorting its appearance. Sometimes the distortion is subtle, a slight stretching or smearing. Other times it's dramatic, producing multiple images or giant arcs of light. By carefully measuring how much the light is bent, astronomers can calculate the total mass of the lensing object, not just the visible mass. The total mass, including everything that contributes to the gravitational field. When they did this for galaxy clusters, the results were unequivocal. The lensing mass was much larger than the visible mass, dark matter again, and the spatial distribution of the lensing mass didn't match the distribution of stars or gas. It was spread out in a diffuse halo, exactly as the rotation curve data suggested. One of the most famous examples is the bullet cluster. It's actually two galaxy clusters that collided with each other a few 100 million years ago and are now passing through one another. When the clusters collided, the hot gas in each cluster, which is ordinary matter, interacted and slowed down. You can see that gas glowing in X-rays, sitting in the middle between the two clusters. But the galaxies themselves, which are mostly empty space, passed right through with almost no interaction. And when astronomers used gravitational lensing to map where most of the mass is, they found that the lensing signal wasn't centered on the hot gas, it was centered on the galaxies. That means most of the mass in the bullet cluster isn't in the gas, it's in invisible halos surrounding the galaxies. Dark matter. The bullet cluster is one of the cleanest pieces of evidence for dark matter because it separates the ordinary matter from the gravitational mass in a way that's hard to explain with any other theory. Then there's the cosmic microwave background, the faint afterglow of the Big Bang. The light that's been traveling through space for more than 13 billion years, carrying information about the state of the universe when it was only 380,000 years old. The temperature of that light isn't perfectly uniform. There are tiny fluctuations, hot spots and cold spots, that correspond to regions of slightly higher or lower density in the early universe. Those density fluctuations are the seeds that eventually grew into galaxies and clusters. Cosmologists can measure the pattern of those fluctuations with exquisite precision and use it to infer the total amount of matter in the universe, both ordinary and dark. The data from satellites like WMAP and Planck show that ordinary matter, the stuff made of protons, neutrons and electrons, makes up only about 5% of the total energy density of the universe. Dark matter makes up about 27%. The rest, about 68%, is something even stranger: dark energy. We'll get to that in a minute. But the point is that the cosmic microwave background gives us an independent measurement of how much dark matter exists, and it agrees with everything else. The rotation curves, the galaxy clusters, the gravitational lensing, all of it points to the same conclusion. The universe is dominated by invisible mass. So what is dark matter? That's the question that's been driving physicists crazy for decades. We know it's there. We know roughly how much of it there is. We know it doesn't emit, absorb, or reflect light. We know it interacts gravitationally with ordinary matter, but we don't know what it's made of. The leading hypothesis is that dark matter is composed of particles that don't interact with light or ordinary matter, except through gravity. These particles are often called WIMPs, weakly interacting massive particles. The idea is that the early universe produced a huge number of these particles during the Big Bang, and they've been floating around ever since, clumping together under gravity and forming the scaffolding on which galaxies and clusters are built. WIMPs would be invisible, but they'd have mass, so they'd exert gravitational pull. And because they don't interact with ordinary matter very much, they'd pass through walls, through planets, through you, without leaving a trace. Billions of dark matter particles could be streaming through your body right now, and you'd never notice. Physicists have built detectors deep underground, shielded from cosmic rays and other background radiation, hoping to catch a WIMP colliding with an atomic nucleus. So far, nothing. No confirmed detections. Decades of searching, and dark matter remains invisible in every sense of the word. There are other candidates, machos, massive compact halo objects. These would be chunks of ordinary matter that just don't shine. Things like brown dwarfs, black holes, or rogue planets floating in the halos of galaxies. Early surveys looked for machos by monitoring millions of stars and watching for gravitational lensing events caused by machos passing in front of them. They found a few events, but not nearly enough to account for all the dark matter. Machos can only explain a tiny fraction of the missing mass. Neutrinos were also considered for a while. These are subatomic particles that barely interact with anything and exist in enormous numbers throughout the universe. But neutrinos have very little mass, and they move too fast to clump together and form the kind of dense halos needed to explain galaxy rotation curves. The bulk of dark matter has to be something else, something cold, meaning it moves slowly, something that can clump, something that's been stable for billions of years, and whatever it is, we haven't found it yet. The fact that we don't know what dark matter is should bother you. This isn't a minor gap in our knowledge. This is 95% of the universe. We've built a cosmological model that works extraordinarily well, that makes predictions we can test, that fits the data from dozens of independent observations. And at the heart of that model is a substance we can't see, can't touch, can't detect directly, and don't understand. We infer its existence entirely from its gravitational effects. It's like being a detective who solved a crime but never found the murder weapon. You know it was there. You know what it did. You just can't put your hands on it. And until we can, there's a piece of the story that's missing. If dark matter is the scaffolding that holds galaxies together, dark energy is the force tearing the universe apart. And it's even more mysterious. The story of dark energy begins in the late 1990s with a question that sounds simple but turned out to have a shocking answer. Is the expansion of the universe slowing down? Ever since Edwin Hubble discovered that galaxies are moving away from each other, cosmologists assumed that the expansion was gradually decelerating. Gravity, after all, is attractive. Every galaxy is pulling on every other galaxy. That pull should be slowing the expansion, maybe even reversing it eventually. The question was how much? Is the deceleration strong enough that the universe will eventually stop expanding and